In this lecture series, we'll take 3 of the reactions that we've seen with alkenes, and we'll see how they extend or apply to alkynes. We'll look at the addition of acids, like HX, and halogens, X2 compounds, like Br2 or Cl2, to alkynes. And we'll look at hydration reactions of alkynes that occur from the addition of acids in water, as in the last example here. And each of these examples will look similar to what we've seen for alkenes, and so we'll focus on the aspects of the reactions that are different for alkynes. First, we'll look at the electrophilic addition of acids of the type HX. HX will add to alkynes to yield alkenes. Here, the X group will add to the more substituted carbon, as with our Markovnikov selectivity. And the H and the X groups will add across the alkene in a trans fashion, meaning that those groups will be on opposite sides of the resulting alkene. Now, in the case of alkenes, the reactions with HX proceed through a carbocation intermediate that forms from the nucleophilic attack of the alkene on the acidic proton of the acid. If we imagine a similar pathway for alkynes, we would form a carbocation on the resulting alkene carbon. This is called a vinylic carbocation, and it's fairly unstable or unfavorable as a carbocation, so alkynes will not react with acids to form carbocations. Because this vinylic carbocation is unstable, alkynes will react with acids in a concerted pathway that avoids formation of a carbocation. Remember that a concerted pathway is one in which the existing bonds break and the new bonds form at the same time, or in a single step. And so here we'll think about this mechanism in the following way. We'll consider the dissociation of HCl in solution to form the chloride anion and a proton. In this way, as the alkyne attacks the proton, instead of forming a carbocation, the chloride anion can attack the electrophilic carbon to form the new carbon-chlorine bond at the same time. This is a little bit of a simplification of the true pathway, but it's a mechanism that helps us account for the regioselectivity that these reactions show. The chlorine, or X group, adds to the more substituted or the more electrophilic carbon. This mechanism also helps us to account for the stereochemistry that these reactions show. The X group and the proton add trans across the alkene. They add to opposite faces of the alkene, and we can see that in this type of a concerted mechanism. One more piece to note here is that this reaction states one equivalent of HCl. But if we were to add a second equivalent, or if we had excess HCl in our reaction, then this alkene could undergo a second electrophilic addition reaction, just as we saw previously, to form the dihalogenated alkane. That addition, as we learned before, also proceeds with Markovnikov selectivity, adding the chlorine or the X group to the more substituted carbon and the hydrogen to the less substituted carbon. Let's try an example. Use the mechanism that we just learned to predict the major products of the reaction shown. In the reaction of an alkyne with HBr, we'll start with the dissociation of the acid into the proton and the bromide anion. The nucleophilic alkyne attacks the proton, and at the same time, the bromide anion attacks the more electrophilic carbon of the alkyne, the carbon that would otherwise become a carbocation. Here the two carbons are equally substituted, so there's no preference for one over the other, and we'll form two products. First, we drew the product where the bromine adds to the left side carbon. That addition occurs with trans selectivity, meaning that the hydrogen and the bromine are added to opposite faces of the alkene. Now we'll draw the product where the bromine adds to the right side carbon, again making sure we draw the appropriate trans addition. So this reaction will form two alkene products that have the bromine in different positions. These are constitutional isomers. Now let's look at the electrophilic addition of a halogen, or X2, to an alkyne. As with acids, the two X groups of the halogen will add across the alkyne, and they will add with trans-selectivity, meaning that the two chlorines here will end up on opposite sides of the alkene. If we add only one equivalent of the halogen, then the reaction will stop here in the middle at the dihalogenated alkene. But as we've seen previously, alkenes react with halogens, and so if we add another equivalent, or we have excess X2 around, or here Cl2, then a second addition can occur. And here, the electrophilic addition of halogen compounds to alkynes proceeds through a pathway that looks a lot like the addition of halogens to alkenes. Remember, with alkenes, we formed a halonium ion intermediate, the three-membered ring with the halogen in it. Here, with alkynes, a similar intermediate forms. The reaction begins with the nucleophilic alkyne attacking the halogen. The lone pair on the halogen, on that chlorine, will attack the other carbon of the alkene to stabilize what would otherwise be a very unstable vinylic carbocation. Then the electrons in the XX bond, or the chlorine-chlorine bond, break and go to the chlorine to form the chloride anion. The chloride anion then attacks the more substituted carbon of the ring. This is the more electrophilic carbon, and the ring opens with the formation of the new carbon-chlorine bond. In this mechanism of ring opening, the attack by the chlorine leads to trans-stereochemistry of the dihalogenated product. From this alkene, if there's another equivalent of chlorine around, then it can add again. And we've seen this mechanism already, but we'll revisit it again here. The alkene attacks the chlorine to form the chloronium ion. And from the chloronium ion, the chloride attacks the more substituted carbon to open the ring and form a new carbon-chlorine bond.